Welcome for the third session of electromagnetic waves 18EC 55. Okay, in this session we are discussing about part 2, that is Coulomb's law and electric field intensity. Myself, Professor Nandisha SP, Associate Professor, Department of E&C, Government Engineering College, Carpet, Mandya District. Okay, in Module 1, the part 2 session is as follows. Introduction to electrostatics, experimental law of Coulomb, definition of electric field intensity, field due to continuous volume charge distribution, field of a line charge, field due to a sheet of charge, definition of electric flux density, and numerical problems. Okay, let us take up the introduction to the electromagnetic waves. See this, the behavior of a physical device subjected to electric field can be studied either by a field approach or by a circuit approach. In circuit approach, we know that the circuit approach uses a discrete circuit parameters like RLC, that is a resistor, inductor and capacitor, passive components, that is RLC passive components, voltage and current sources. At higher frequencies, the frequency in the megahertz or gigahertz, parameters no longer be a discrete. They become non-linear also, depending on the material property and strength of voltage V and I associated. This makes a circuit approach to be difficult and may not give a very accurate results. Thus, at higher frequencies, the field approach is necessary to get a better understanding of the performance of the device. Okay, in the simple ways, we are see that if the frequency of the a signal, normally in our India, the line frequency is 50 Hz from the power station, and we generally know that if frequency of the signal goes on increases, the current is tried to flow in the outer surfaces or outer boundaries of the conductors. Okay, this phenomena is generally called as a skin effect. At certain frequencies, starting from the center of the conductor to surface of the conductor, current flows. If the frequency is above the some specified value, without the help of the conductor, the current is flows. The value of the current is in the microamps and nanoamps. Suppose if the strength of the current is more, it harms to humans being. That is why the value in the field, it should be order of micro or nanoamperes. Let us see the objective of this chapter, that is introduction to electromagnetics. That is, electrostatic deals with the case in which the electric charges are stationary. When the charges are stationary, the electric field set up by them remains static. That is, whatever the magnitudes and directions the field has at the different points in the space around the charges will remain unchanged with the time. Hence, the name electrostatics. Finally, you can simply, in the simple words, you can say that the charges in the static positions, okay, deals with the electrostatics. In electrostatics, Coulomb's law plays a very important role. When the charges involved could be approximated to a point charge. The charges may be taken in different forms, that is point charge, line charge, surface charge, volume charge, etc. But especially in the Coulomb's law deals with point charges. Therefore, here we are understand the Coulomb's law. Also, the conditions under which there could be what we call a point charges. In the Coulomb's law, that deals only a point charges. Okay, let us see the definition of the Coulomb's law. Coulomb's law states that force between the two very small objects separated in a vacuum or a free space by a distance which is large compared to their size of the charge, proportional to the charge on each and inversely proportional to square of the distance between them. See here, F is directly proportional to Q1 into Q2 divided by R square. The basic formula is F directly proportional to Q1 Q2 divided by R square. F is equal to Q1 F proportional to. First you are defined a proportional to, there we define a proportionality constant K. F proportional to Q1 and Q2 divided by R square. Then taking the proportionality constant K is equal to 1 divided by 4 pi epsilon naught. Then proportionality is changed to equality. Okay, the constant K is placing here. See here, F equal to K into, this K is a proportionality constant into Q1 Q2 divided by R square, where Q1 and Q2 are the positive or negative charge of the point charges of the charge measured in coulombs. C. R is the separation distance measured in meters. Proportionality constant K is equal to 1 divided by 4 pi epsilon. That epsilon is the permittivity, free space permittivity. The value of epsilon naught is 8.854 into 10 raised to minus 12 farads per meter. See, the quantity epsilon naught is not a dimensionless for Coulomb's law, shows that it has the label Coulomb square per Newton meter square. Then Coulomb's law now we defined is, after substituting the value of K, F equal to Q1 Q2 divided by 4 pi epsilon naught R square Newton. See here, charge Q1, charge Q2. The force between charge Q1 Q2 is equal to this formula. This formula, Newton. See, if Q1 and Q2 has a like signs, the vector force F2 on Q2 is in the same direction as the vector 1, 2. If the Q1 and Q2 has like sign, both are positive charges, Q1 and Q2 are positive charges. Now this vector gives the final result of FQ. Now after defining the Coulomb's law, this is the general form of the Coulomb's law. F is equal to Q1 into Q2 divided by 4 pi epsilon naught R square Newton. This is the general formula. Now this is the vector form of the Coulomb's law. Vector form of the Coulomb's law. In vector form of the Coulomb's law indicates that in a particular direction the vector operates. F2, see here, F2, here F2 is there. Okay. In the particular direction the vector force is existing. This is R12 is equal to R2 minus R1. This is R2 minus R1. This is the R2 vector, this is the R1. R12 is equal to R2 minus R1. See this? This is a A12 is a unit vector. Here A12 is the unit vector in the direction of R12. Unit vector can be find out magnitude of R12 divided by modulus of R12. R12 divided by modulus of R12, that is R12 is nothing but R2 minus R1, modulus of R2 minus R1. This is the value of the unit vector. Now you can see the force expressed by the Coulomb's law is a mutual force. For each of the two charges experiences a force of the same magnitude, although of opposite direction. We might equally well have written in the Coulomb's law in linear form as follows: F1 is equal to minus F2. F1, okay, F1 is equal to minus F2. Suppose F1 value Q1 Q2 divided by 4 pi epsilon naught R square into A12. A12 vector from one left side to right side, A12. F2 minus F2. This minus sign is decided by the direction of the unit vector. See, these are unit vector A21. From 2 to one side, in the opposite side, the vector is moving. That is why this is a linear. F1 is equal to minus F2 is equal to Q1 Q2 divided by 4 pi epsilon naught R square into A12 is equal to Q1 Q2 divided by 4 pi epsilon naught R square into A21 Newton. Now this is a formula for the Coulomb's law in the vector form. In vector form, addition to Coulomb's law, we are having a vector that gives the direction. Now let us define electric field intensity. Okay, for defining electric field intensity, let us consider a one charge is at fixed position, say Q1, and one charge is moving around the charge Q1. That moving charge is called as a test charge or a second charge. By present of second charge around the first charge, displaying a existence of a force field. Call this second charge as a test charge Qt. Therefore, by the Coulomb's law, you can write it as test force equal to force F is equal to, see here, F suffix T. Okay, force due to test charge on Q1, that is F is equal to Q1 into Qt divided by 4 pi epsilon naught R square 1 T, where Qt is the test charge and A1T is a unit vector from the test charge to a charge Q1 Newton. Let us writing this force per unit charge Ft divided by Qt is equal to Q1 divided by 4 pi epsilon naught R square 1T into A1T. Now force per charge is nothing but electric field intensity, that is the field intensity by a single charge is nothing but electric field intensity. See this? We define the electric field intensity as a vector force on a unit positive test charge. Unit positive test charge. See, electric field intensity is denoted by capital E. Electric field intensity is equal to force charge divided by force on the test charge divided by test charge. Ft by Qt is nothing but electric field intensity. Call this equation as 7. See, equation 7 gives the definition of the electric field intensity, and equation 8 gives the expression for the field intensity due to a single point charge Q1 in vacuum. See here, E is equal to electric field intensity, E is equal to Q1 divided by 4 pi epsilon naught R square 1T into AT. Okay, here R is the magnitude of the vector R, the directed line segment from the point to which the point charge Q is located to the point at E is desired, where AR is the unit vector in the direction of R. See that A1T is the test charge direction, and this test charge direction is replaced by unit vector AR. Then E is equal to Q1 divided by 4 pi epsilon naught R square into AR. See this? This is the origin point. This is the Q point. This is the point P, where this vector E indicates the electric field intensity. Okay, this is the vector R. Now this is the vector R dash. Capital R is equal to R minus R dash. See this? The vector R dash locates at the point Q. The vector R identifies the general point in space P, XYZ, and the vector R from Q to P, R from P to Q is that Px is then R minus R dash here. The above equation can be expressed in the general form for a single point charge is ER is equal to Q1 divided by 4 pi epsilon naught R minus R1 whole square into A1 is the unit vector. Okay, this is for a single charge electric field intensity due to a single point charge. Similarly, for n number of point charges, you can write it as Q1 divided by this much, Q1 divided by 4 pi epsilon naught into R minus R1 square plus Q2 divided by 4 pi epsilon naught R minus R square into A12 plus Q1 divided by 4 pi epsilon naught R minus R1 square A1 an1. By adding or by summing the all n number of point charges, you can have electric field intensity for the n point sources is given by qm divided by 4 pi epsilon naught r minus rm whole square into am. This is a formula for the electric field intensity due to a n number of point charges. Okay, let us discuss a field of a line charge. Now here we discussed field of a single point charge. Okay, the point charges is taken into account. Field due to a single point charge q1. Here field due to a line of charge. A line of charge. See here. First let us understand what is meant by line charge and how it will be existing. See here, this is a rho L is a line charge. This is a line charge over which a small portion of the charge is marked here. Okay, in line charge only one parameter is existing, that is the, see here, this is x direction, this is y direction, and this is z direction. If you understand this figure and write it in proper way and understanding these parameters and writing the line charge here, it is a very important concept to analyze and obtain the value of the field of a line charge. See here, there is a x field, x axis, y axis and z axis. In the z axis the line charge is placed and the name of the line charge is rho L. Rho L indicates that line charge, line charge density, rho L, over which this is placed. At z axis some point dq is taken. dq is a small fraction of the point, or it is equivalent to a point charge, you can say, because line is made up of point charges only. Line of charges, and line is formed by point number of point charges. Okay, in the z axis we are taking a small fraction, that is dq is equal, because this is a differential charge dq over the line charge. Because of this line charge in the z direction, rho L into dz. Z is a z axis. In order to differentiate this axis z and this point z, this is taken as z dash. This is taken as z dash. That is the, we are writing dq is equal to rho L into dz. This is the value. Okay, this is a, here is a unit vector. This indicates the direction of the line charge. This is the direction of the line charge. Let us consider a point P over the y axis. This DE rho exists here, DEZ exists here. The diagonal value D is given. See here, DE is equal to DE rho into A rho plus DEZ into AZ to the electric field intensity produced by the an element of charge dq, that is rho L into dz, located in the distance z r dash from the origin. The linear charge density is uniform and extending along the entire z axis. See this? Now to find the incremental field, or a incremental field, or a small field, or a differential field, any name you can call it as. To find the incremental field P due to a incremental charge dq. See here, dq is equal to rho L z dash. See here, dq is equal to rho L z dash. We have dE, that is here dE, diagonal value for the point to be considered is P. dE is equal to rho L dz minus r dash divided by 4 pi epsilon naught r square, where r is a r minus r dash square. Already 1 r is there, into r square gives the r minus r dash cube, where r is equal to y into ay, that is equal to rho into a rho, that is r dash is equal to z dash into az, and r minus r dash is equal to rho into a rho minus z dash into az. Substituting all these points, we are going to get dE is equal to rho L into dz into rho a rho minus z dash into az divided by 4 pi epsilon naught into rho square minus z dash whole square to the power of 3 by 2. Since only e rho component is present, because only in the z direction only e rho component is present, and simplifying this one we get dE rho is equal to rho L into rho dz dash divided by 4 pi epsilon naught rho square plus z dash whole to the power of 3 by 2. Okay, now a line charge is taken from minus infinity to plus infinity. Now E rho is equal to integral minus infinity to plus infinity rho L into dz divided by 4 pi epsilon naught rho square minus z dash whole square to the power of 3 by 2. Integrating by the integral table or change of variable, that is z dash is equal to rho into cot theta. We have E rho is equal to rho L divided by 4 pi epsilon naught rho into 1 by rho square into z dash divided by square root of rho square minus z dash whole square, ranging from minus infinity to plus infinity, and E rho is obtained after simplification. E rho is equal to rho L divided by 2 pi epsilon naught into rho. This is the field existing for the line charge. See that this is the same equation expressed using the vector form. E rho is equal to rho L divided by 2 pi epsilon naught rho into a rho. See that we note that field falls off inversely with the distance to be charged line as compared with the point charge. See, in the point charge 1 by 4 is there, here for line charge 1 by 2 is there, where the field is decreased with the square of the distance. Thank you very much. Thank you very much.